To hold all your math awards, you need a cardboard box with volume 28,000 cubic centimeters and no lid. But cardboard is expensive and you're not made of money, so you decide to use as little cardboard as possible. Use Lagrange multipliers to find the dimensions that minimize the amount of cardboard used. So here's your cardboard box. I drew this ahead of time. I drew it with no lid. The problem does state no lid. So let's label the dimensions. The length dimension, well, let's call it the depth dimension, x. And then the height dimension I'll call z. And then this width I'll call y. And we know that the volume you could write as x times y times z. And we know that that's 28,000 cubic centimeters. But that's not what we're trying to minimize. We're trying to minimize the surface area. So let's call the surface area function f. So it's f of x, y, z technically. And f of x, y, z, okay, it would be, if you just find the area of all the faces of the box, there's only 5 faces because there is no lid, then that'll be the surface area. So let's do the bottom face first, y times x. Y times x would be the area of the bottom face. The area of the side face, the right side face would be x times z. The left side face would be x times z as well. So we have 2 of those. So we have plus 2 times x times z. So I'm building the surface area formula. And then finally, there's the front face and the back face, which have the same area, y times z. So I'm going to add in 2 times y times z. And that would get you the surface area. So the idea then is to minimize f using Lagrange multipliers. Well, the technique of Lagrange multipliers says first find del f, set it equal to lambda del g, whatever that is. Well, let's focus on del f first. Del f, okay, so we need, for the first component, the derivative of f with respect to x. So that's going to be, derivative of this guy is with respect to x is y. Derivative of this guy with respect to x is 2z. So y plus 2z, okay, times I. There's your first component. And then your second component, derivative of this guy with respect to y. We need the derivative of the whole thing, f with respect to y for the second component. That's x. The derivative of 2x times z with respect to y is 0. And then the derivative of 2yz with respect to y would be just plus 2z. And that's times j. Plus the derivative of f with respect to z. Okay, derivative of this guy with respect to z is 0. Derivative of this guy, the derivative of this guy with respect to z is just 2x. The derivative of this guy with respect to z is 2y. So 2x plus 2y would be the third component, call it the k component. And then the thing we call g is, technically you have to set this equal to 0 to get it. So it'd be x times y times z minus 28,000 equals 0. So technically this guy would be g of x, y, z. But I mean, if you didn't set it equal to 0, you'd still get the right answer because minus 28,000 is a constant. Anyway, let's do del g first. Del g would be equal to just y times z for the first component, derivative with respect to x. The derivative with respect to y for the second component would be x times z. So you get x plus x times z j. Then the derivative with respect to z for the third component would be x times y, so plus x times y k. Then remember, we need to set del f equal to lambda del g because they're scalar multiples of each other. So let's multiply through by lambda. And we get lambda yz for the first component, lambda xz for the second, lambda xy for the third. And then remember, we set up a system of equations. Okay, let me make some more screen real estate here. So the system of equations that we solve to get critical points or point, maybe there's only one critical point here. Okay, we set corresponding components equal to get those equations. So the first equation would be y plus 2z is equal to lambda times y times z. The second equation would be x plus 2z, set that component, the j component in del f, to the j component in lambda del g, which is lambda x times z. And then the third component, or third equation rather, you'd get by setting the third components equal. So 2x plus 2y is equal to lambda x times y. And then you really should include what we call the constraint equation. I'm going to use the first version of it. X times y times z is equal to 28,000. So you solve this system of equations, and that will yield one or more critical values that could be your dimensions in this case that minimize the amount of cardboard used. So one assumption I can make immediately, I can assume that x, y, and z, none of them are equal to 0. Otherwise, if one of them were 0, your box wouldn't have any volume. So they have to be non-zero. So that allows me in the first three equations to solve for lambda. So and then set the results equal. So I can say lambda from the first equation is equal to y plus 2z divided by y times z. And from the second equation, lambda is x plus 2z over x times z. And from the third equation, I get that lambda is equal to 2x plus 2y over x times y. And then let me shrink this down a little bit. From this first equality, I can go ahead and multiply through by z and get these guys to divide out just to simplify it. And if I do that, I actually get y plus 2z over y is equal to x plus 2z over x. And from that, I'm going to cross multiply. So x times the quantity y plus 2z and y times the quantity x plus 2z. And if I do that, let me go up here. If I do that, and distribute, I actually get x times y plus 2xz is equal to x times y plus 2yz. And then if I subtract x times y from both sides of this resulting equation, and then divide both sides by the 2 and the z, I end up with a pretty significant result. X must equal y. The x and y dimensions must be equal. And then I can do something similar for this other equality down here. So focus on this. First off, I can multiply through by x. And so the x's are gone, in other words. And I get x plus 2z over z is equal to 2x plus 2y over y. And if I cross multiply, much like I did above, I'll get x times y plus 2yz is equal to 2xz plus 2yz. And so I get some nice results here. I can subtract 2yz from both sides. And then after that, divide out the x's, and I get y is equal to 2z as a result, which is another significant result. And then let me make some more real estate here. And then I can now look at the third equation. Since x is equal to y, I can replace x with 2z, and I can replace y with 2z to get, okay, the x would be 2z, so 2z times the y would be 2z, so 2z times the z that's still there is equal to 28,000. So I get an equation with one unknown in it, and I can solve. So I actually get 4z cubed is equal to 28,000, or z cubed is equal to 7,000. If you take the cubed root and factor it out, you'd get 1,000 times 7, so you can bring out the cubed root of 1,000 is 10. So 10 cubed root 7, that's centimeters, right? And then we know y and x are double that. So we can say that, if I scroll down, we can say that x is equal to 20 cubed root 7 centimeters, and y is equal to, same thing, 20 cubed root 7 centimeters. Now this is the only critical point we get, x, y, z, so I would argue it has to be the solution, because just by the nature of the problem, the surface area should have a minimum. It won't have a maximum, because you could always make one dimension smaller and one dimension larger and get as much surface area as you want, as much cardboard as you want, to create a volume of 28,000 cubic centimeters. But just by its nature, it should have a minimum. So I'm going to say, and by the way, Lagrange multipliers will yield that minimum if it exists. So I'm going to say that the dimensions are 10. No, let's go with the x dimension first. So 20 cubed root 7 by 20 cubed root 7 by 10 cubed root 7. And these are all in centimeters.